Hello, ladies and gents, and this is the January 2013 paper for D1. Okay, with the D1 exam up next week on the Friday afternoon, I believe. Okay, so this isn't a very popular question, but they have had a couple of them. So what we need to do is we need to use a flowchart, and we've got to use these values. Oh, hello. We've got to use these values down here. And it says work into at least 7 decimal places. Give the final output correct 7 decimal places as well. So the first thing we did, so start. We're then going to go on to this one here. So input n and e. So n is 72 and then e is 8. We then move on through the flowchart, which is down here. R equals n over e plus e divided by 2. So that's what you need to do. You need to do 72 divided by 8 plus 8 divided by 2. And we get 8. Sorry, we get 8.5. Now, is our takeaway E? So our takeaway E is going to be 0.5. Is that in between this value and this value? So these values are minus 0.000001 and 0.000001. So when they say is our takeaway E, basically they're saying is the difference between these two numbers less than this value here or greater than this value here. In which case, no, it's not. 0.5 is way above the second one here. So, nope. So because we've got, come down here, and because it's no, we say that E equals R. So E now equals 8.5. Then we go back up here and we repeat the process. So then R equals N divided by E. So we're going to do 72 divided by 8.5 plus 8.5 divided by 2. So 72 divided by 8.5 plus 8.5 divided by 2, and we get 8.485294118. Is the difference between that less than this? No, it is not. So we then, so because it's no, we now let E equal R. So all we're doing is we're just following the flowchart around over and over again. So we're now going up here. I've now let in, we're doing N divided by the new value of E plus the value of E. Dividing it by 2, and for that we get 72 divided by our answer plus our answer divided by 2 gives us 8.485281374. So it's quite a small gap. If we have a look here, if we do this one, take away that one, we get 0.000012. So therefore, no, it's not between these two values. So no, and we keep going again. So 8.485281374. And then we repeat the process. It's quite a long-winded approach for 4 marks, but if we do that, we get 8.485281374, which is identical to what we got last time. So yes. So if it's yes, we put output as R. So I will then say that the final output is a value of R. So the output is 8.485281374. Okay, now if we do this part B, describe how this would affect the output if we have n is 72 and e is minus 8. So if we did e as minus 8, we'd actually get minus 8.5. And so all you do is you'd find the negative square root. So you would find negative square root. Take the value of e, which cannot be used when using this flowchart. So let's have a look at how we use e. And we've got n divided by e as the first part here. So if we've got n divided by e, you can't divide by 0. So therefore e can't be 0. And that's it. That's our first 6 marks. Okay, so let's have a look at the next question. Oh, clearing on both pages. Starting with the list of all the letters of the alphabet in alphabetical, just demonstrate how binary search is used to locate the letter P. In each iteration, you must make clear your pivot and the part you are retaining. So with a binary search, it's important to make sure you've got a numbered list. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Look at that. Again, through the magic of editing, I'm going to pause the video while I write in the letters just to save you a little bit of time. Hello. Okay, and there we go. Okay, so starting with a list of all the letters of the alphabet in alphabetical order, demonstrate how binary search is used to locate the letter P. So with a binary search, what we do is we do the first number in the list plus the last number in the list divided by 2, and then if you need to round it, you always round it up. So I would say, and I make sure you write this down as well, 26 plus 1 divided by 2, and that would lead to that's going to make 13.5, so that's going to be the 14th piece, which is n. 14th piece, n. So I'd say that P is after n, so reject 1 to 14. So now we're rejecting 1 to 14. These ones here have all gone. So the next one I'll do is I'll do 15 plus 26 divided by 2. So that's going to be 15 plus 26 is 41 divided by 2 is 20.5, so that's going to go to 21, which is U. So P before U. So therefore reject 21 to 26. So then we're left with 15 plus 20 divided by 2, which goes to the 18th piece of data, which is R. P for R. So reject 18 to 20. So then we do 15 plus 17 divided by 2, which equals 16, which is P. So letter found. That's how you do that one. I mean, with this one, it's just a matter of repeating the process, and as long as you've done a couple of these questions, it really is quite easy. You've got to make sure you repeat the process. So find the maximum number of iterations needed to locate any particular letter of the alphabet. Justify your answer. Okay, so remember that we're going to get rid of one more than half of the amount each time. So let's say we've got the 14th piece here, which was n. So then we're going to get rid of, also it's not one more than half, is it? We're going to get rid of 15 through to 26. So that would be one iteration. So then you're going to do 1 plus 14 divided by 15, which is going to be 7.5, which is going to be 8. So if we pick H, no, sorry, my mistake. Sorry. Ignore that bit. So let's say we do the first bit again. So 1 plus 26 divided by 2 is going to give us the 14th piece of data. So therefore, if it's after n, we're going to reject n everything forward. If it's before n, we're going to reject n and everything afterwards. So you're only going to be left with 13 pieces of data. So that's going to be one iteration. Then you're going to do, let's continue the way we did it. So we do 15 plus 26 divided by 2. So now we're going to get rid of another half. That's going to be a second iteration. Then we're going to get rid of another half of the data. And if we get rid of half the data and it's an odd number, then we're going to need to get rid of an extra one as well. So for instance, we've got 15 plus 20 divided by 2 is 17.5, which goes to 18. So we're going to get rid of these three here. So we always get rid of half the data. So that's the third one, leaving us with a gap of 3. So if we had P, that's going to be selected straight away. If we've got either O or Q, we're going to do another iteration. So let's say we get rid of, let's say it's before P, so therefore we're going to get rid of those two. So we're going to be left with 1. So it's going to be 4 iterations. So we're going to get rid of half each time, and possibly just one more than half. So the way the mark scheme talks about this, maximum 5 iterations. Oh no, yeah, sorry, 4 iterations gave us P, so we then need to do a 5th iteration to get to either O or Q, whichever one we chose. So the maximum letter Z at the start of each letter is 26, 13, 6, 3, and then 1. Okay. So question 3 is the matchings question. Okay. So matchings questions. Starting from the initial matching, so figure 3, this is the initial matching here, or this one here. And use the maximum matching algorithm to find an improved matching. So what we're going to do is we're going to start from C, and we're going to try and get to either 1 or 2. So we're going to start from C, and the only one that C can be matched to is 4. But using the initial matching here, whenever we use the initial matching, we've got to go, when we go from right to left, we've got to go on the one they've already used. So that's already connected to N. N has to go to 6. And 6 has to go to J. And then J can go to 3. Go to 3. And then 3 is already attached to R. And R can go to 2. In which case, breakthrough. Because we've got to an unmatched vertice or vertex there. So just to make that a little bit clearer, when we use the initial matching, we start off by choosing an unmatched arc, also an unmatched vertex, which is C, and then we go from left to right on any that we choose, but whenever we go from right to left, we've got to go along an existing matching. So we've gone from C to 4, and then 4 is already attached to N, so we've got to go back along N. And then we went from N to 6, then 6 is already matched to J, so we've got to go back there. Then we've got to go to 3, 3 is already matched to R, and R can go to 2 to get a breakthrough, because that's an unmatched arc there. Once we've got a breakthrough, we need to change, it's good to write this, change status. Don't give anyone any reason to take any marks away from you. So change status, C now attaches to 4. 4 doesn't attach to anymore, but N attaches to 6. J attaches to 3. And R attaches to 2. So that's the alternating path, and now list your improved matching. So now, if we do the improved matching, If we have a look at what we've done so far over here, we haven't touched G. So when we've gone from right to left, we've got rid of R to 3, we've got rid of 6 to J, and got rid of from N to 4. So what we're going to do is we've already got this one. So now C now goes to 4, N goes to 6, J goes to 3, and R goes to 2. So now what we do is we write the improved matching. So improved matching, we write down C4, G5, J3, N6, that should be J3, put comma in there accidentally, J3, N6, and R2. So I'm having a mare with my commas. There you go. So that is the improved matching. Explain why it's not possible to find a complete matching. Again, they ask us pretty much every time. And what you've got to do is you've got to look for the vertices. If you have a look here on the left-hand side, find the vertices that will only match to 1. Then what will happen is that they both only match to the same vertex. Now, we need someone to do both, someone to do task 1 and to do task 5, but the only person available to do task 1 and task 5 is G, and G can only do one of them. So what you need to say is that G is the only person that's available, George is the only person that's available to do task 1 and task 5. That's why it's not possible. Okay, next one, it says, after training, Charlie adds task 5 to his possible allocation. So what we do is we go back to our original diagram and we say that Charlie can now do 5. Charlie. Okay, taking the improved matching found in A as the new initial matching, use the maximum matching algorithm. So what they've just said, what they mean by that is, if we get rid of the blue ones here, if we get rid of it and just start it again on a new grid, our um, our matching was C to 4, G to 5, J to 3, N6, and R2. So to get a complete match, we've got to match O to 1. We do it in exactly the same way as before. And now we've got this extra arc here from C to 5. So we're going to start off with O, and we're going to use our maximum matching algorithm. So O, we can match that to 6. O's got to be matched to 6, which is already matched to N. And we can, so O to 6, got to go to N. N's got to go to 4. And then 4's already matched to C. We can now, C can go to 5. And 5 is already matched to G. And G can go to 1. In which case we say it's a breakthrough. And fish off and breakthrough. And then we change the status. So O now goes to 6. N goes to 4. C goes to 5. And G goes to 1. And then what I'd probably do, just to make it clear to myself, is I'd write down the new, or I'd do the new matching. So now O goes to 6, N goes to 4, C goes to 5, and G goes to 1. If we have a look on the previous ones, we didn't touch J to 3, so that stays the same. We didn't touch R to 2, so that stays the same. And that is our complete matching. And then what we've got to do, have a look down here, give the alternating path and list your complete matching. So you've got to write down complete matching and write them down. So C5, G1, J3, M4, O6. I'll just look at my commas there. No issues anymore. And that's it. That is our complete matching. Question 4. So we're doing okay. I think this is quicker than my previous paper I did. But the trouble is about decision maths, it does take quite a while. Right, okay. I'm just going to pause the video so that I can rotate this around. I'm not a dumb man, but sometimes I do struggle. I think it's me getting old, which sucks. Anyway, explain what is meant in a network by the term path. Now, this is a bit of an odd question, really, because in terms of doing revision, because if they've asked you to define the term path once, they probably won't ask you to do it again. They'll ask you to define a different term. And what I'll try and do is in the comments box or in some box, I'll try and do a list of all the definitions. I'll have a look on the internet see if I can put that there. But path is it's a sequence of arcs, so it's a sequence of arcs which connect vertices where no vertex appears more than once and the end of one arc leads to the beginning of the next arc. Let's have a look, see what they say about that one. I've never done too sure on definitions. So finite sequence of edges such that the end vertex of one edge appears at the end of the sequence is the start of the vertex of the next, and which no vertex appears more than once. So what we've got to do for this, 1 3 points made clearly, all 3 points made clearly. So sequence of arcs or edges. I didn't say finite, and so you might need to use the word finite in there. But if it's a sequence of arcs which connects with this end of one is the beginning of the other one and no vertex appears more than once, that's what you need to do to get all the marks for that one. Okay, so now we've got to use Dijkstra's algorithm now. I really like this one. So they even give you this here, which I think is really helpful. So the order of labeling, we always stick this as the first one. And just to make sure that we get all the marks, we write a working value of 0 for the first one, which I've never done in the past, but always do it. So we've just labelled this one as a permanent one, or as a final value. So now what we do is we do everything coming off S. So that's going to be 14, 5, and 12. And then the smallest one that we've labelled gets a permanent label. So that's the second one we've labelled, and we're going to call that one 5. Now everything coming off B, we add on the arc. So 5 plus the 8 is 13. 5 plus 22 is 27. And that's everything coming off B. So now what we do is we have a look at all of the temporary values. And we've got A, D, and C, which haven't been labelled yet. So C gives us the smallest working value, so therefore that's the next one that we made permanent. Basically what that means is that we can't get to C any quicker than 12 minutes or whatever. It turns out to be 12 miles. Obviously it's length in miles, so it's 12 miles. So now we have a look. So we've just made this one permanent, so now we add 25 and 13 to C, so 12 plus 25 makes us a working value of 37 there. 12 plus 13 is 25 for D. And now we have a look. So we've got working values of 37, 25, and 13. So 13 is the smallest one. So that's the next one that we label. And now everything coming off A, we've got 18 here. So 13 plus 18 is 31. 13 plus 11 is 24. Look at that. And now we have a look at all the ones that aren't permanent yet. And the smallest one is D, so that's going to be the 5th one. And we make that 24, and we do everything coming off D. So 24 plus 5 is 29. 24 plus 18 is 42. 24 plus 8 is 32. And then we have a look at the smallest. So the smallest is 29 here. So that's the next one we do. So we make that one permanent. So that's the sixth one. We call that 29. So 29 plus 12 is 41. And that's it. That's the only thing coming off there. So now what we need to do is sorry, looks like 25 then. Needs to make sure it's 29. The next smallest temporary one is 32. So we're going to make that permanent. So that's our seventh one, which is 32. And everything coming off 32 is going to be 40, which makes this one our eighth and final one. That's 40. So the shortest spot, how do we get from S to T? And what we do is we count back. So we have a look at the permanent ones. 40 take away 12 isn't 29. 40 take away 18 isn't 24. 40 take away 8 is 32. So we use that path. 32 take away 25 isn't 12. 32 take away 8 is 24. And then we keep going back this way. So 24 take away 13 isn't 12. 24 take away 5 isn't 29. 24 take away 11 is 13. So if we work back that way, that is going to be our shortest path. So S, B, A, D, E, T. And the shortest path is 40. So write down the length of the shortest path from S to F. So F, if you have a look at the final value here, this final value is represents the shortest time that it takes to get from the beginning back to there. So that is simply 29. Next, with the canal represented by arc AB is closed, so that one is closed. Find the shortest path from S to T, avoiding AB, and state its length. So we can't go along this bit anymore. So we have a look at the alternatives. So we could get to A at 13, and then we can't because this one's closed. We can get to that one, instead of by 13, we get that by 14, and then, so if we go this way, then this way, this way, this way, we're only adding on one there. Of course, we could go other ways, and what we've got to do is try and find the shortest way. So, there are actually two ways of getting to D by only one more than the original 24. We can go S to A to D, which makes it 25. We can go S to C to D, which is also 25. So we can go either one of those. So and that only adds on an extra 1. So I'd probably go S, C, D, E, T, and that's one of 41. Or we could have gone S, A, D, E, T. That's also 41. Let's just double check. Yep, SADET or SCDET of length 41. Hooray. Okay, next one, question 5. Now this one is Prim's algorithm. Oh, this. Okay, see how this works. So counterclockwise, oh, I love it. Question 5. Nice and easy. Right. So use Prim's algorithm starting at A. So when we do Prim's algorithm, in fact, what I would do, I don't know if they've got it here to help us. No, they haven't. Is just so that we can see this. I often just do the vertices, so A, C, B. You don't need to do this. I kind of like doing it this way just because 1. And I like doing dots to dots, obviously as a kid. I had so many friends. G and J. But also helps you see where the loops are occurring. So what we do is we're starting from A, so we've got to find the shortest arc that comes off A. So that's going to be A to C. And now what we do is we see the shortest arc that's connected to either A or C. So we've done that one there. So the shortest one coming off that, we've got 50 here, we've got 14, 20, we've got 35. So the shortest one is going to be 14. So C to F is going to be the next one. So we need to write them down in order. It says you must stay in order in which you include the arcs. So in order it's going to be AC, then we chose CF, and the shortest one connecting to either AC or CF, we've got this one here, DF, which is 12. The shortest one connecting to any of those so far, 50, 20, 38, we've got this one here which is 17, I believe is the next shortest, F to E. So E to F or F to E, which is 17. Then we have a look at the next shortest, which I believe is E to B, or B to E. Now the next shortest that's connected to any of them, we haven't done any on the right hand side of the graph yet, so F to I looks like the next shortest. So F to I is 18. Then the next shortest, we've got this tiny one here, I to J, which is 10. And then J to G, which is 9. And then the only one that we haven't got connected yet is H, so the shortest one is going to be D to H. We don't do any rejections, that's Kruskal's algorithm, but that's it. So that is the minimum connector for the network. So what I'd also do is I'll just work out the cost there, even though it doesn't ask for it, it's always worth doing it just in case. So we add up AC, and we add up all the rest of them as well. So 32 plus 14 plus 15 plus 17 plus 12 plus 19 plus 18 plus 10 plus 9 equals 146. Given that, in fact, what we'll do is I'll sketch it on here, just so we can check the answer in a second. Given that it costs £80 per kilometre to keep station roads open in winter, calculate the minimum cost of ensuring roads access to all the Warden stations. So it's 146 miles or kilometres, and it's going to cost £80 per kilometre. So you do 146 times by 80, which gives us £11,680. Okay, next one. At the end of winter, Ben inspect. Oh wow. What I'll do just quickly is I'll just make sure that we've got these questions right by having a look. So 11,680, what we've got there, and then ACE. So we've got AC, CF, DF, EF, BE, FI, IJ, JG, or GJ, and DH. Doesn't matter which way around you write it. Then 146 times by 80 is 11,680. My confidence has been rocked since one of my students, thank you Ellen, told me that I got question 4 wrong in the last one. So my apologies for the last video, but thank you very much Ellen for pointing it out to me. Okay, next one is route inspection. Now route inspection, if you've done your research and so if you've done your homework, very, very easy again. What you've got to do is you've got to have a look and find all the vertices where you've got an odd number or an odd valency. So here we've got H, which is 3, we've got I, which is 4, we've got J, which is 2, G, which is 3, 1, 2, 3, 4 for E, 1, 2, 3 for B, and 1, 2, 3, 4 for C, F, 1, 2, 3, 4, 5, 6, and F's got 7. So route inspection, we need to find find the four, and there'll always be four vertices. So you find the four vertices where there's an odd number of arcs going into it, and then we do all the combinations. So we can do BF and HG. We can do BH and FG. We can do BG and FH. And what we've got to do is we've got to find the shortest route which connects B to F. So the shortest route, by the way, almost certainly won't be the direct route. So if we're trying to find the shortest route which connects B to F, don't just look for the shortest route. So don't just look for the most direct route because it won't be the shortest. 15 plus 17 is 32. We've got 34 that way, 38 this way. So I think 32 is the shortest route to get from B to F. From H to G, we've got 21 plus 41, or we could have gone down there and up there. So that's going to be 40. Could go around the houses there, so that's 30. What now? That's too much. 25, no, that's too much. So yeah, 40, it looks, is the shortest one. That's down here, and up there. So that's a total for that one of 72. Next, we try and have a look at B to H. So B to H is, we could go here to here to here. So that's 32.57. Or we could go there to there to there, which is 60. I think that's it. I think 57 is the shortest one to get from B to H. I stand to be corrected, of course. Then F to G, the shortest way is, we could go 17 to 24, which is 41. We could go 18, 28, 37, so I think 37 for that one. That's going to be 94. I can't see a shorter way to get from F to G. And then B to G, the next one. B to G, go 15 and then 24, so that's going to be 39. So that's that one there. I don't think there's a shorter way. And then F to H, simply that one there, that is the shortest way, and that's 25. So that's going to be 59, 64. So that there is going to be the shortest way of connecting up B, G, F and H using route inspection. So using route inspection, find the roads that we traversed twice. So when we did this, we traversed B to E twice, and then E to G again, and we've done F to H again. Find the length of the shortest inspection route, because it says he'll start and finish at A. Now what this means is that we need to make the, in order to start and end at the same point, we can't have any odd arcs. So we can't have any odd vertices. So here, you've got an odd valency for H. What we need to do, we linked up F and H again, and then by doing that, what we've done is we've said, even though we've gone down that road twice, if we add in that road as an extra road, now H has got a valency of 4, which is even, and F has got a valency of 1, 2, 3, 4, 5, 6, 7, 8, which is even. And by doing the same for B to G, which was there and then there, now B's got a valency of 4, E's got a valency, we've added 2 to E, so that's still even, and G's got a valency of 4, because we've got 4 arcs going into it, so now they're all even, which means you can go around the whole route inspection, the whole graph, starting and ending at A, because all of them have got an even valency. So what we do is we add up the original, which is 379, plus the ones that we've got to go down twice, which is this one, and this one. So that adds on another 64. So 379 plus 64, 383, 443. So that's going to be the length of the shortest inspection route. Okay, so the next one, if Ben starts and finishes his inspection route at different warden stations, a shorter inspection route is possible. So now, what it's saying is that we could start at A, then end at D. So that's when it's called semi-traversal or semi-Eulerian. And what we can do with that, it means that we can start at one of the odd ones. So the odd ones are here, 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 and here. We can start at one of the odd ones and finish at another odd one. And what we've got to do is we've got to, I've just realised that I've rubbed out all my workings. Um, we've got to find out the shortest way of getting between any of the two. So I can't, if I have a look at my scheme, um, so here, these were the workings that we had, and the shortest route between any of them is F to H. F to H was only 25. So what that means, if we go back to our question here, F to H was only 25. Well, actually, it's double make sure, yeah, 443, 443, yeah, we got it right. So F to H, if we join those two up, now this one's even, this one's even. So the only two odd ones are B and G, which means that we can start at B and end at G, and therefore we've gone round all of the different roads, but the only one that we've had to go through twice is this F to H one, which means that we only need to do an extra 25. So determine the two warden stations Ben should choose as start and finishing point. That's B and G because we've managed to link up the other two for only an extra 25. Give a reason for the Ben should choose a start and finishing point in order that his route has minimum length. Give a reason for your answer. So the reason is that that's the shortest way to connect up two of the odd valencies. And give a reason for your answer. State the length of the route. So the route is 379, and the only one we've got to add on is this extra 25. So if we add on 25 to 379, we get 404, which 404. So Ben should choose to repeat FH since this is the shortest. He could choose B and G as the start and finish university. So yeah, that's pretty much exactly what we said. Okay, next one. Next one is one that no one likes doing very much, but it's okay. It's not awful. So in fact, I'm going to try and make it a little bit bigger. So Lefner is producing floral arrangements for an award ceremony. He'll produce two types of arrangements, celebration and party. Let X be the celebration arrangements made, let Y be the number of party arrangements made. Figure 6 shows three constraints other than X and Y greater than 0. The rejected region has been shaded. Given that two of the three constraints are Y is less than or equal to 30, so that's going through, this is the line Y equals 30, so it's that constraint. X is less than or equal to 60, so X equals 60 is that one there. Write down as an inequality the third constraint, so we need to work out what the equation of that line is. So we're all big enough and ugly enough, hopefully now, to work out the gradient of a line. So we need to find 2 points that line the line, this one here and this one here, and we've got to work out the gradient. So the change in height is 10, change in distance is 50. So the gradient is y equals 10 over 50, or 1 over 5x, and then plus c, so plus where it goes through the y-axis, which is 0. So we just got y equals a fifth x. Now, we have got to, that's not an inequality though, that's just the equation of this line. So what we've got to do is we've got to see whether it's y is greater than or equal to a fifth over x, or y is less than or equal to a fifth of x. So what we do is we choose 2 points, one either side of the line. So let's choose this one here, let's choose this one here. So this one is 0, 20, and this one is 60, or 60, 0. So let's have a look. The x coordinate is 60 and the y coordinate is 0. So a fifth of 60 is 12. Is 12 less than, sorry, is 0 greater than 12? Or is 0 less than or equal to 12? So this one is correct. This one, 0 is not greater than 12, so that one is incorrect. So therefore this is the correct one. So we know that y is less than or equal to 1/5 of x, or x over 5. Okay, each celebration includes 2 white roses and 4 red roses. Each arrangement includes 1 white rose and 5 red roses. Leffner wishes to use at least 70 white roses and 200 red roses. Write down 2 further inequalities to represent this information. So, if we have a look at what x and y were, so celebration, we've got 2 white roses and 4 red roses to make that. So, if we do our x number times 2, that's how many white roses we're going to do. If we add to that our party celebrations, which is y, and we times that by 1, that's going to be the number of white roses that we use. Now we've got to use at least 70 white roses, so that's got to be 70 or greater. So we write down that 2x plus y is greater than or equal to 70. Let's have a look at the red roses. So the x celebrations, each celebration has 4 red roses, so times that by 4, and that's how many red roses we're going to use. So the number of celebrations, which is x, times by 4. If we add to that the number of party times by 5, so that's going to be y times by 5, and we've got to use at least 200. So that's going to be greater than or equal to 200. So 4x plus 5y is greater than or equal to 200. And those are 2 inequalities. Add 2 lines and shade them to diagram 1 to represent these 2. So what we've got to do is we've now got to put on these 2 lines. So if you're going to do 2x plus y greater than or equal to 0, and 4x plus 5y is greater than or equal to 200, what we tend to do for these ones is sort of, so if we choose the top one first of all, we need to find 2 coordinates that lie on this line, so it's greater than or equal to 70. So I could have x as 35 and y as 0, or I could have x as 0 and y as 70. So if we do that, 0, 35 and 0, 70, so 35, 0 and 0, 70, and then we join them up. Let's see whether or not this ruler works for my screen. Ish, yeah. Right, okay, now it's got to be greater than 70. So we choose 2 random points. Let's choose 0, 0 and loads. So is 2 lots of 0 plus 0 greater than 70? No, it's not, so we don't want that one. Is 2 lots of 60 plus 70 greater than 70? Yes, it is. So we want this side of it. We do not want this side of it. So let's shade that one out there. Okay, next one, 4x plus 5y is greater than or equal to 200. So what we do is we find out values of x and y that make that one correct. So I'm going to change colour. So I could have x as 50 and y as 0, or I could have x as 0 and y as 40. So 50, 0 and 0, 40 are those points there. Let's join them up. Now we need to be bigger than 200, so again, choose 2 points, choose these ones here. 4 lots of 0 plus 5 lots of 0 is not greater than 200, so we do not want this side. 4 lots of 60 plus 5 lots of 70 is way bigger than 200, so we do not want this side of the line here. So we've done this one. Hence determine the feasible region and label it R. So the feasible region is this one here. So that's going to be R. Time taken to produce each celebration arrangement and each party arrangement are 10 minutes and 4 minutes respectively. Lessner wishes to minimize the total time taken to produce the arrangement. Write down the objective function. So she wishes to minimize t, which is 10 minutes for every x, so 10x, and 4 minutes for every y. That's what she wants to do. Use point testing to find the optimal number of each type of arrangements Lethner should produce and find the total time she will take. Right, okay, so if we are now going to do this here, let's find a number that both 10 and 4 go into. So let's say 400. Let's say we want to have the time as 400 minutes. Now I could do x as 40 minutes. I mean, I've just chosen 400 completely randomly because I know that 10 and 4 both go into it. So I could have 40 minutes and 0, so x is 40, y is 0. Or I could have x is 0 and y is 100, which I can't do actually. Let's have y as 50 and x is 20. That one works. So if I do 40, 0 and 20, 50, is that there? So this here is my objective. Or not. Let's try that again. This here is my objective line. And if I push this line this way, I'm going to find the maximum. If I push it this way, I'm going to find the minimum. So she wants to optimize, so she wants to minimize, so therefore I'm going to need to push it this direction. So if I keep going down, I end up getting to this point here. So I need to find out where this line here and this line meet. So this line here that we drew was 2x plus y is greater than 70. So we know if those two are going to meet, then y is 30. So we'd say that y equals 30. And if y equals 30, 2x must be 40, so x equals 20. So that is the optimum number of each that she needs to make, and the total time that would take. We know that each value of x takes 10 minutes, so that's going to be 200 minutes. And each value of y takes 4 minutes, so 30 times by 4 is going to be 120, so that's going to be 320 minutes. So if we have a look at the mark scheme, so that's our feasible region R. So we've got it there. Let's have a quick look at this just before we mark it. Okay, so yeah, the way we did it was absolutely fine. As long as we've written that x is 20, y is 30, and 320 is written there. Condone lack of or incorrect units of time. Okay, question 7. This is our final question, so for 16 marks. So yes, we've rattled through this one. I'm going to say we, thinking that I've done the majority of the work for this. I'm sure you guys have done your bit as well. Okay, so we have got critical path analysis. So activity network in relation to building projects, the activities are represented by the arcs. The number in brackets on each arc is the time given to complete the activity. Each activity requires one worker. The project must be completed in the shortest possible time. So just bear with me a second. I'm going to need to do a Gantt chart in a sec. Explain the reason for the dotted line from event 4 to event 6. So event 4, if you have a look up here, event 4 was this one, event 6 was this one. Okay, so why did we need that there? There's two reasons why you would need a dummy arc, and that's each activity needs to have its own distinct start and end, or different um, different activities are dependent on different preceding activities. So if we have a look here, I is only dependent, so here I is only dependent on F and B, but K is dependent on F, B, and E. So that's what you need to say. So you need to say that I dependent on just F and B, but K, we're on the same line if I were you, dependent on E, F, and B. Okay, part B, complete diagram 1 in the answer book, show clearly early event times and late event times. So, we start off with 0 here. So what's the shortest time that A can be done? It's got to be 9. The shortest one D can be done in is 6. The shortest one this one could be done in isn't 11, because that can't, nothing can start at 11, because D and G have both got to finish first. So that one is going to be 12. Just like this one here isn't 10, because A and F have both got to finish before this one can start. So therefore that's going to be 16. So therefore, if this one takes another 4 minutes, but this one has got to take 60 minutes, so that one is going to be 16 minutes because this one's got to have finished first. If we have a look at this one here, that's going to be 14 because G, that one can start at 12, but if we have finished H won't have finished until 14. So this one here, by the time I's finished, that's going to be 19. By the time J's finished, it's going to be 16. So 19 is the earliest at which everything has been finished. And finally, if we have a look at this, once K's done, that's going to be 20 minutes. Once L's done, it's going to be 21 minutes. By this time, it's going to be 17 minutes. So 21 is the earliest everything's going to be done by. So now what we do is we start at 21 and then we work backwards. So we can start this one at 17 minutes so that it takes 4 minutes and then it's still done for 21. This one has got to start on 19 minutes so that it's done for 21. M can start on 18 minutes and still be done by 21. And keep going, working backwards. So this one here has got to start at 19. No, sorry, has got to start at 16. So that this one is done for 19. This one here, it's got to be done in time for 19, it's got to be done in time for 18. So we can't start this one at 18 because it's going to take 4 minutes to do this one. But we can start that one at 15. So if we start this one at 15, it's going to take 4 minutes to do J, and that can still be done for 19. So let's just make that one clear, that's 18 there. G, it can start at 9 to do this one in time for 15. And it can start at 9, and it's going to take 17 minutes to do that one. So yeah, so that one can start at 9. We can't start this one at 10, even though this one down here would be done for 18. This one wouldn't be done for 15. So we can't start that one at 10, it's got to be 9. This one here at the top, it can start at 13 to get this one done for 17, but it can't start at 13, take 7 minutes and be done for 16. So that one's got to be 9. And the first one always goes back to 0. Let's just double check that we got that one right. So 9, 9, 6, 9, 16, 16, 20, 12 and 15. Yep. 16, 17, 19, 19, 14, 18. Yeah, look at that. Make it look. Hello. That's right. Sorry, that was lovely Mr. Graves coming in to see me. So question C, state the critical activities. So critical activities are ones where there's no float. So here, if we have a look at A can start at 0, and it can end at 9, but it's only got 9 minutes, so there's no lag time. You can't start at 1 minute, so you're not going to have any spare time to do that. So A is a critical activity. B, however, it could start at 0 and end at 16, but it's only going to take 10 minutes. So we've got days, whatever it takes, whatever the units are. So here we've actually got an extra 6 minutes in which we can do B. So B isn't a critical activity. C could start at 0, end at 15. So we've got 15 minutes to do that, but it's only going to take 11. So C isn't critical. Similarly with D, D can start at 0, end at 9. So it's got 9 minutes to do it, but it's only going to take 6 minutes, so it's not critical. A critical one is where, like A, you've got 9 minutes to do it, and it's going to take 9 minutes to do. So with G, can start at 6, end at 15. So you've got 9 minutes to do that, but it's going to take 6 minutes, so no, it's not critical. H can start at 6, end at 18, so you've got 12 minutes, it's only going to take 8, so that's not critical. J can start at 12, end at 19, so you've got 7 minutes, it's going to take 4, so that's not critical. M can start at 14, end at 21, so you've got 7 minutes, it's only going to take 3, not a problem. E can start at 9 and end at 17, so you've got 8 minutes, it's only going to take 4, that's not critical. F can start at 9 and end at 16, so you've got 7 minutes, and it's going to take 7 minutes, that is a critical activity. I can start at 16, end at 19, which gives you 3 minutes, and it's only going to take 3 minutes. So that's going to be I. K can start at 16, end at 21, so that's 5 minutes. It's only going to take 4 minutes, so you've got 1 minute to play with there. Finally, L, so that's not critical, sorry. And L, it can start at 19, end at 21, so you've got 2 minutes, and it's going to take 2 minutes. So L is also a critical activity. So those are critical activities there. Say the total float for activity G. So as we said, G down here can start at 6 and end at 15. So you've got 9 minutes to do that one. So in terms of doing your calculations, I do, because you've got 2 marks here, 15 take away 6, which leaves us 9, and then take away the duration of the activity, so 9 take away 6, leaves you a total float of 3 minutes, or 3 whatever it is. Draw a Gantt chart for this project on the grid provided in the answer book. Okay, I'm going to need to use this here, so I'm going to use the answer book for this one. So 14. So let's draw a Gantt chart. Now, when you draw a Gantt chart, or a cascade chart, they sometimes call it, what you need to do is you need to do the critical path. So the critical path was this activity, this activity, this activity, and this one here. So that was A is the first one, so 8 to 9. And then from 9 to 16 was F. From this one to this one is I, so that's I is 16 to 19. And then L is from 19 to 21. Lovely. So now that's that one done, that one done, that one done, that one done. So let's go with, actually let's make that one red so we don't make any mistakes. So let's go B now. B can start at 0 and it's going to take 10 minutes. What we do, so it's going to take 10 minutes, so that goes to there. But in theory, we could end at 16. So what we do is we do a dotted box up to 16. So that's that one done. C can start at 0 and it takes 11 minutes. So C up to 11 minutes, and that can go up to 15. That's when it can end. So let's go up to 15. D, 0 to 6, and then that could go up to 9. E is the next one. So E can start at 9, and then N, and it's going to take 4, so E can start at 9. It's going to take 4, so it takes up to 13. However, it can go up to 17. F's already done. G can start at 6, and then it's going to take 6 minutes, so that's going to go up to 12. But it can end at 15, so let's... H can start at 6. We start H here, and that's going to take 8 minutes, so that goes up to 14. However, it could go on to 18. I've already done. J can start at 12, and it's going to take 4. And of course, that can go up to 19. Next one is K, which can start at 16. It's going to take 4. And of course, K can go up to 21. L's already been done, and then finally M. M can start at 14. It's going to take 3 minutes. It takes up to 17. And of course, M can go up to 21, can finish at 21 as well. So that's how we do the Gantt chart there. Things that must be happening at 5.5. So if we draw a line at 5.5 minutes, so A has got to be happening because A doesn't move, so A has to be happening. When's the latest D can start? So this, and this, they can't start at 5.5 minutes or 5 minutes, so they can't be happening. So it's whether or not B has to be happening. So B, if you can end at 16, it's going to take 10 minutes. Therefore, you could start at 6 minutes. So B doesn't need to be happening. C needs to end at 15 minutes, and it's going to take 11 minutes. So you've got to start that at 4 minutes to get it done. So therefore, the later C can start at 4 minutes, so it's definitely going to be happening at 5.5 minutes. Similarly with D, D has got to end by 9 minutes unless it's going to cause a delay. So D's got to be done by 9 minutes, which means the latest it can start is 3 minutes, which means at 5.5 minutes, D is definitely going to be happening. And that's it. Right, so we've got part G here. I don't need to use too much more. So G. Use your Gantt chart to determine the minimum number of workers needed. The minimum number of workers need to complete the project in the minimum time. You must justify your answer. So you're going to need to have at least 3 workers because A, C, and D must be happening at that time. So, is there any time that you've got to have at least 4 activities going on? So what we could do is have a look at 9.5 minutes here. Do we have a look at 9.5 minutes? Do we have to have all those activities? F's got to be happening. So F's got to be happening. And imagine this B here, the fact that you can slide it up and down is always going to be overlapping that 9.5 minutes. If we go back to our diagram, which we haven't got now, here we go. So if we have a look at B, B has got to be started by 6 minutes. So B is going to be happening at 9.5 minutes. C's got to start at 4 minutes, so C is going to be happening. D doesn't need to be happening. Does E need to be happening at 9.5 minutes? So E, no, we can start E at 13 minutes. What about G? So G is going to take 6 minutes. So if it's got to start by 15 at the late, so it's got to end by 15 at the latest. It's got to start at 9 at the latest. So at 9.5 minutes, yeah, G is definitely going to be working. So that's 4 workers, unless it's going to cause a delay. So what about H? H is going to be H can start at 10 minutes, so H doesn't need to start. So we're going to need 4 workers to start for. So there are going to be 4 activities that need to be happening at 9.5 minutes, and then what we do is we see whether or not there are any other lines that we can draw, so that all the other ones have to be working at the same time. And the answer is no. There's no other lines that we could draw anywhere, so that we need to have those workers working. So if we look at this, so activities F, B, C and G together, they've all got to be happening between 9 and 10, so therefore 4 workers are needed. So the minimum for this one is going to be 4 workers, because at that time, remember, this here is the allotted time so that it doesn't cause any delay to the activity. So between 9 and 10 here, all of these activities have got to be going on, so therefore we're going to need a minimum of 4 workers, one to do each one of these tasks. Okay, thank you very much. Hopefully there wasn't any mistakes that time round. Thank you very much. Like, subscribe and share. Good luck revising.